Hey guys, so now we have already stretched the endpoints of our Fourier series to minus L to L. Let's just go through an example on how we're going to do it. Now I would like to stress that most of the functions that we encounter would be defined from minus L to L, not minus pi to pi. So it's good that we have a good grasp of the technique, or at least look through an example and know certain terms that we need to be very careful when we do the algebra. Now as you know, getting Fourier series involves integration. The function are multiplied by the cosine function, so cosine and sine function. So we need to be really careful of how we do the integration, as well as taking advantage of the odd and even properties. Sorry that I'm talking too much, but let's go to the example. Okay, the objective is to find the Fourier series of the function x equals to x squared on minus 3 to 3. So now, as you can see, the endpoints have already changed. And basically, yes, we do calculate the Fourier coefficients. Fourier coefficients of a0 is going to be equals to 1 divided by 2l. Recognize again that there's a 2 here, divided by l, integrate minus l to l. The limits have changed to the endpoints of the function f of x. I've written this out so you can see the whole formula. We do the application, which is very easy. Okay, so this is equal to 3. Now, next we move to find the Fourier coefficient of an. Okay, so the Fourier coefficient of an is 1 divided by l now. Be careful, it's not 2l, it's changed to l. Integrate minus l to l, the function multiplied by the cosine n pi x divided by l. So it's n pi x divided by l. Basically, how I look at it, you can try to, if this helps you remind you on why is it n pi x divided by l. Basically, the transformation of the variable comes from the n divided by l. The n and the x stays the same, but you got the pi and you got the l because we're going from pi and then we're going to l. So that's why we got the pi there and we got to divide by l. Okay, that's just a way for me to remember. Then later when you put in the numbers, okay, so this from here to here we're going to go to basic application. There's no surprise about that. And after this we get this thing over here. So how am I going to integrate this? Okay, we got x squared multiplied by the cosine n pi x divided by l. Well, it's just basically using integration by parts. So if we can re-represent this as an antiderivative, which we have done over here, later we can differentiate the x squared. And when we differentiate the x squared, it's very easy because we have reduced the degree. That is definitely progress. So this one becomes over here. Basically, these two is already evaluated. I think I said this a lot of times. Okay, and we are left with this integration over here. Now, what can I say? This is what I can say. Always notice that if we were to substitute the limits, right, into a sine function, okay, there's a lot of chances that this would cancel out to be 0, okay? Why did I say that? Well, because you see, notice that if I substitute 3 inside, this will get sine n pi. Sine n pi, negative or positive is always equals to 0, so sine n pi gets cancelled out. But you need to be very careful of the x squared. Okay? You need to be very careful of the x squared because sometimes we are substituting inside 0. In this case, it's not. It's something 3 and negative 3. However, what I can say is that this whole thing was still equal to 0 because when we substitute 3 inside here, I'll get a 3 and this thing over here, right? Okay, basically it's also get 0, but be mindful of the x squared. If I substitute negative 3, it's negative 3 squared, so I will get 3 minus the same thing, okay, which is equal to 0. So what I can say is that I'm left with evaluating this integral, which I've written over here. I brought out the constants and, just to make it a bit neat. Again, another integration by parts, and this time it goes to this over here, okay, and then from here, now I can immediately write the same process. I get this thing over here, and minus, okay, let's give it minus, integrate 0 to 3, but I got a negative sign, so that's why it becomes a plus, okay, so this is the thing that I have, and again, what is the shortcut that I can employ? The shortcut I can employ is that when I integrate a cosine function, I will get a sine function n pi x. Well, after that, when I get the sine function and the n pi x, right? I substitute 3 or I substitute 0, it's going to give me a sine n pi, and that's going to be equal to 0. So I will be very quick to just immediately cancel out this term. But this can only work if this is a constant, okay? This is a constant. We're not integrating this with respect to x. So this is a constant, that's why it can work. Basically, what I'm trying to say is that you will get a certain n pi x divided by 3. And you need to evaluate this. However, when you put the limits, you divide by 3, you get 0. So just cancel this out. Integrating a constant, okay, in the cosine function, most chances you will get 0. But again, you need to be careful of the limits, okay? It's just a guide. Don't take it as a rule, but take it as a guide. So evaluating this is no problem, this is what we have. And lastly, the Fourier series of the function of f of x is f of x where x is x squared. The function f of x is x squared is given by this thing over here. And basically I've written out like this. Why? Because now is the time to go into the real meat of the problem of whether the Fourier series converges to the function f of x. Using this as a prime example, we are now moving, this is going to be a background for our study of convergence that is coming up next. Okay, notice this thing over here. Let x equals to 3. If x is equal to 3, the Fourier series becomes 3 plus summation n equals to 1 to infinity. Now, what can we notice? Notice that if x equals to 3, this one becomes cosine n pi. Cosine n pi becomes negative 1 to the power of n. So this becomes negative 1 to the power of n. I will multiply this with this. So I will still have the 36 divided by n squared divided by pi squared, and I'll have a negative 1 to n. Okay. The thing I noticed that negative 1 to the power of 2n is always, this is going to be always to an even power. So basically this becomes now 1. Right. So now what we have is that we can kind of postulate, okay, we can kind of postulate, but we don't know for sure whether this thing tends towards 0. Well, certainly we know that when x is equal to 3, the function f of x is equal to 9, right? So when x is equal to 3, the function f of x is equal to 9, 3 squared. However, it seems a bit cloudy right now on what this summation is. We still cannot know. Now, I must like to add that you can do your individual analysis on the summation and get possibly, and I say get possibly, x equals to 6. Okay, so 6 plus 3 we get 9, that's fine. But it's still a bit confusing at the moment. Now, when x is equals to 3 divided by 2, what is the Fourier series? Well, the Fourier series, if I can write it out very quickly, is basically going to be equals to cosine n pi divided by 2. Now, this is going to be even more unclear because cosine n pi divided by 2 can become negative 1, it can be 0, and it can become 1. So, we still do not know that when this changes to negative 1, 0, or 1, and we take the summation and multiply by this term over here, we still do not know whether this would give us 9 divided by 4. Well, certainly the function f of x is equals to 9 divided by 4. So, it's still unclear to us. Okay? Lastly, if I have the function f of x is equals to x, the Fourier series is going to be given to, very quickly, n equals to 1 to infinity, 6 n pi minus 1 n plus 1 sine n pi divided by x. 3, sorry. Okay, so if this is another function that I have, and obviously x is integral from minus 3 to 3, this is a Fourier series. Now, let's look at this very carefully. If x is equals to 3, okay, this is not, I'm using another function over here. If x equals to 3, function f of x is equal to 3. No surprise about that. However, the Fourier series is going to give me 0. Can we see that? Substitute x equals to 3 inside, the sine function gets eliminated. So basically you are taking the summation of 0, this is what you have. So obviously in this case, we see that the Fourier series does not agree. Does not agree in this case explicitly. Now, this one is still a bit cloudy. We still do not know, whether is it 9 divided by 4 when we take the summation. And certainly this one is also very unclear because it's 3 and we need to know that this summation is equal to 6. So what I can tell you right now is that when we go from the function to the Fourier series, it is very unclear. And this is the basis for the convergence theorem, which is coming up in the next video. This is grounds to say that there definitely needs to be a way to see whether the Fourier series converges. So yeah, the Fourier series converges to the function because here are certain points which they do not, okay, or which they clearly do, or we clearly do not know. Okay, so theorem, our convergence theorem coming up.